All right. How's it going, Professor Lehman? My name is Nathan Reynolds. I am in your ME360 class. And one sec, just grabbing some notes. Cool. And this is my video presentation on the problem that you gave us about the stream function of, sorry, I'm just going to draw the problem real quick. So it looks like what you gave us is a flow going downwards, and then there's a source. Here. I'm going to draw. So this is X, this is Y. We have a flow going down. Like so. And in figure A, it's showing just the flow going up against a flat plate, and it kind of goes out like this, which makes sense. All right. But also states that we have a source right here, which is exerting a liquid that creates a half body, like so, with a height h for this hump kind of thing. And basically, this creates a stagnation point right here. All right. In the problem, it states that the potential flow against a flat plate can be described with the stream function psi equals a x y. And also, we know from the book and also the notes that you gave us that the stream function for a source is equal to m over 2 pi theta. And we know from superposition that the total potential flow or stream function is equal to the uniform flow plus the source. So we have a x y plus m over 2 pi times theta. Since this part is in polar or cylindrical coordinates, I'm going to convert this part, the uniform flow, into cylindrical coordinates, just so that way we're working in cylindrical the whole way through. So, x and y are going to be the same as saying r cosine theta and sine cosine theta. So continue on, we get psi equals a times r cosine theta times r sine theta plus m over 2 pi theta. Now, this right here is a trig identity. It's base one would be 2 sine 2x is equal to 2 sine x cosine x. So we use that And basically a stays the same, r squared, and then we have sine 2 theta. And due to the original trig identity, it's going to be over 2. And then the second part stays the same. All right. So, hold on. Scroll down a little bit. All right, we also know that v sub r, or the radial velocity, is equal to 1 over r of the derivative of your stream's function in relation to theta. So really we just take the derivative of this up here. So we get 1 over r, r squared stays the same because it's in relation to theta. Sine of 2 theta, sine of theta is cosine theta, so cosine of 2 theta times 2. So this 2 would cancel out, so it's just cosine of 2 theta plus m over 2 theta times theta. Again, you take the derivative with respect to theta, the theta drops out, it just becomes m over 2 pi. That cancels out, and we're left with just VR, radial velocity, equals a r cosine 2 theta plus m over 2 pi. All right. We also know that, or we can also find the angular velocity, or v sub theta, and that's going to equal the negative derivative of psi times dr, because we know from a flow diagram or a flow field that if we have du dx and dv dy equals 0, so that would mean that one of them would have to be negative. So v theta equals negative d psi dr. Once again, taking the partial derivative of the psi equation, this time with respect to r. So we get negative a, the derivative of r squared is 2r. That cancels that 2, so it's just r times sine of 2 theta. That doesn't change. And then it's plus a constant. The constant drops out. So we're left with just v sub theta equals a, or negative a r 2 sine theta. All right. And in the problem, it said determine the relationship between bump height, h constant a, and source strength m. This equation only has a. It does not have the source strength or the height in relation. So we're going to plug our values into our v sub r equation. Doing that. So at the stagnation point, we know that, let's go back up. At the stagnation point, we know that theta is equal to pi over 2 because it's going straight up. R is equal to h, height, and also that v sub r is 0, and v sub theta is also 0 because SX stagnation. So it's not moving radially or angularly, I guess. Yeah, so R is equal to, or H is equal to R, and theta is equal to pi over 2 because it's at 90 degrees. All right, now that we have that, we can plug this in and say V sub R is equal to 0, or 0 is equal to A times R, which is H cosine of 2 pi over 2, theta is at pi over 2, plus M over, oh, wait. Right, yeah, so I multiplied this 1 over R through here, but I forgot to multiply it all the way through. So 1 over R. So it becomes M 2 pi over R. Coming back to where we were. Wait, what? Partial derivative squared. Yeah, okay, no, that's right. I just forgot to multiply the R all the way through. That's my bad. I got a little confused. So M over 2 pi R. M over 2 pi R over here, but plugging it in as H. All right, so we basically have a relationship that compares area, height, and the source strength. So we can just move some stuff around. Oh, cosine of pi is -1. So this is negative AH plus M over 2 pi over H. Move this over to the other side. Just add, because this is already negative, H area times height equals source strength M over 2 pi H. This can become H squared. This can become M over 2 pi A. Oh, and this isn't area. This is just a constant. I don't know if I mentioned that. But yeah, that's how we get our relationship between bump height H, the constant A, and the source strength M. Yeah, so basically, used our stream functions for steady flow or uniform flow and a source, and then we converted to polar coordinates all the way through, and then we used the velocity, the radial velocity, and the angular velocity, even though we really didn't need this. Found how that relates to the radius A and the source strength, and then we just substituted in our variables for the specific stagnation point that we were looking for, which was at theta equals pi over 2, R equals H, and that gave us this relationship, H squared equals M over 2 pi A. All right, should wrap it up. Thank you for listening. Have a good night.